Hi everyone. In today's video, we have a new question in the topic of ship stability. And in this question, we'll focus on finding the effect of the free surface on the ship's overall kg and gm. This question is taken from Captain Subramaniam's ship stability series. This is exercise 10, question number 9. If you do not have the book, don't worry about it. I have the question here and the solution as well for you. Alright, so let's get started. The question says there is a vessel which has two deep tanks, port and starboard. Each tank is 12 meters long, 5 meters wide and 8 meters deep. The port side tank is full of seawater, while the starboard side is empty. The displacement is given as 9840 tons, km 8.5 and kg 8 meters. You have to calculate the GM fluid, that is the GM after you apply the free surface correction, if seawater is transferred from port to starboard until each tank has an equal quantity of ballast. Alright, so remember this is seawater, density of seawater is 1.025. So let's get started with the solution. But before I start with today's solution, I want you to be able to draw whatever you have read here and understand what exactly is going on. Alright, so let's start drawing. And like I always say, don't have to draw very fancy diagrams. As long as you understand what's going on, that's good enough. Alright, so we'll have two deep tanks. These are the two deep tanks. And the length of the deep tank is 12 meters long, so each deep tank is 12 meters long. Alright, we'll call this starboard and we'll call this port, and it's 5 meter wide and it's 8 meters deep. Alright, so this is very important, 8 meters deep. And the deep tank was filled, the port side, remember, is full of seawater, so all this is full of seawater, while the starboard is empty. Right, now remember that you have transferred water from port to starboard until each tank has equal quantity of ballast. That means both the tanks have the same quantity. That means if port tank is full, then you have transferred till the port side has become half, so that port and starboard both have half the tank amount of water in it. Alright, so what I will do is I will erase half of the tank, alright, assuming, and here also I just, you know what is port and starboard, so this is port and this is starboard, so I will just assume that here, somewhere here is half of the tank, and now starboard is half full as well. Alright, so both tanks are now equal quantity of water, both of them have half quantity. Alright, so you have to understand now how the shift in the center of gravity of the shifted water has taken place. Alright, so the water from port to starboard has been shifted. We'll calculate the amount and everything later on, but right now you have to understand what is the center of gravity of the shifted water. How will you calculate that? Alright, so let's understand this. So we've got 8 meters of depth of tank. So if I break it up, so now you've got half a tank full of water, right? So the total depth of the tank is 8 meters, remember that. But now you have filled it up to 4 meters each, 4 meters, right? Now the water which was originally here, the center of gravity of that water was in the center here, so this is also 4 meters, right? So if this was here, so half of the 4 meters, this much is 2 meters, plus this 4 meters is 6 meters, and the water currently which has been transferred, this has been transferred here. Here the center of gravity is half of the depth, which is 2 meters. Alright, Now when you use the GG1 formula, because this is only a single weight transfer, we'll use a GG1 formula. So remember, the formula is W by D divided by displacement, because the displacement remains the same. We'll calculate W later, but this D here, this D is, in case of shifting, is the difference in the center of gravity of the shifted cargo from its initial position to the final position. So initial position was 6 meters, 4 plus 2, see the port side tank. So the original amount of water sitting here, water from here shifted here, right? So the original was 6 meters, and now the currently it is 2 meters on the starboard side. So this becomes 4 meters. All right, now let's find out the weight of the water shifted. So how can I find out the weight of the water shifted? So weight of the water shifted will be length by breadth by depth of the tank multiplied by density of the water in it, which is equal to 12 by 5 by 8 meters multiplied by 1.025. all right, now this is not weight, this is the total weight in port tank. So this is equal to 492 tons. all right, weight of water, weight of, sorry, as I am writing I get disoriented sometimes. So weight of water shifted from port to starboard, shifted from port to starboard, equals 492 tons, because exactly half of it was shifted, divided by 2, which is nothing but 246 tons. So this becomes 246 tons, right? And you know displacement is given to you already, it's 9840. So GG1 will be equal to 4 times 246 divided by 9840, which is 0.10 meters. Now when the water has shifted from a higher place to a lower place, naturally on the ship, if you are on the ship here, this is the overall ship, right? And this is K and this is G. Now any weight which has shifted downwards will pull the center of gravity towards the shift. So in this case the water shifted downwards, as you can see, from port to starboard. So the center of gravity of the ship will also come down, right? So if you've got GG1 as K 0.10, the original kg of the vessel is 8 meters. GG1 shifted downwards is 0.10, so it will bring the kg down, so kg value will reduce. So kg after shift is 7.90 meters, right? So now let's take km. Km is 8.50 meters and kg is 7.90 meters. Km minus kg will give you the gm, but this gm is solid, gm solid, 0.600 meters, right? So to this we have to apply free surface correction. Why? Now as you probably know, free surface correction, or free surface effect rather, arises from half empty tanks. So in full empty or tanks which are full, there is no free surface effect, but here there are two tanks now which are half empty. That means water is now sloshing about, it is freely flowing, because of which free surface effect adds. So there are two tanks here, so I have to calculate the free surface effect of both tanks, or we can calculate for one tank and then multiply it by 2. all right, so free surface correction for port tank, let's say, will be LB cube by 12 multiplied by density of the liquid in the tank divided by displacement of the tank, or displacement of the ship. So LB cube by 12 means length of the vessel, length of the tank multiplied by cube of the breadth of the tank divided by 12, which is a constant. Density of liquid inside the tank is 1.025 because it was filled with seawater, and displacement is given to us as 9840. So free surface correction you will find is 0.013, but this is only for port tank. Now because both tanks are half empty, you will just, so total free surface correction for port and starboard tanks will be equal to 0.013 multiplied by 2, which is equal to 0.026 meters. This is the total, because there are two tanks. Now if there was one tank only which is half full, the other was either empty or full, then you would only consider the free surface correction for one tank only. Now let's go back to where our GM solid was. And remember, GM solid was 0.600 meters. If I apply my free surface correction, which is always a subtracted, it's always subtracted, 0.026 meters, then my GM fluid is the final GM, will be 0.574 meters, which is the correct answer. All right, so let me know what you thought about this video. Remember to draw diagrams and understand conceptually what is going on, otherwise you will struggle in the exam. All right, if you have any questions, any concerns, queries, comments, you can write it in the comment section below, and I'll see you soon with my next video. Bye for now.